So let's continue with Professor Papadogiannis. Professor Papadogiannis, I call him Nectarios because also he's a friend of mine, very good friend of mine from the old days of the university. After I was undergraduate, he was an example of a PhD student. Actually, he was one of the best graduates of the physics department in Crete. He is the first PhD in ultra-fast laser pulses. And we are going to see, I think that we are going to enjoy his seminar course in ultra-fast laser NanoAcoustics. So, Nectarios, the floor is yours. Actually, he's a great football player also. So, he's a multi-talented. So, let's welcome Nectarios.
Thank you very much, Kostas. The physics department win basketball with Kostas at football by me. I mean, 30 years ago. Okay, so thank you very much, the organizers, for invite me here, and also I'd like to be that I'm very glad to be again here after many years at Politecnico in Milano, that I like very much the place and the people here. So now we change topic. Actually, we remain in ultrafast laser pulses, but we just explore an application of this kind of pulses in the use of them to prepare very, very high frequency and high intensity and intense nanoacoustic strains, and some uses of these strains in material diagnosis. First of all, the motivation is the miniature sonars, the physics and the technology back of that. So the main idea back to optoacoustics is the effect that was first observed in lower frequencies, of course, in 19th century by the Alexander Graham Bell, when shown a modulated beam of sunlight on material, on selenium material, where they observed that they can induce mechanical waves using light. Now, nowadays, we can have a short laser pulse, and which can be periodic, for example, train of pulses or even single pulse. And we shown this pulse onto an opaque material like a solid. The light is converted into burst of sounds, or sometimes single fast N-type, for example, sound, and the sudden heating produced by light expands or contracts the material in the region of illumination, and there is a hot volume of solid which is near the surface, for example, if the material is opaque, and then we have a sound wave drive outwards of the interaction region outside of the material that shown by the laser. So there is a sound which reflected from defects, from interfaces, from all region of the solid, that there is different acoustical impedance, and arrive again in the surface, where we can probe them simply with another laser, for example, or other instrument, and do actually this that I promised to you, the miniature sonar. Now, the nowadays state of the art of this field is with ultra-fast femtosecond laser pulses, for example, that we can generate and detect, of course, mechanical acoustical strains in the order of gigahertz up to terahertz, from certain cases, which correspond in a solid of a mechanical wave that have a wavelength only a few microns, even few nanometers. So we have a mechanical strain with the abilities in imaging of a soft X-ray or an X-ray pulse. Now, miniature sonar system use this nanoacoustic technology to eavesdrop on sound passing through, for example, atomic cracks, ultra-thin films, or minute nanostructures. Since the whole measurement typically takes place only a few tenths of picosecond, this takes the name in the bibliography as ultrafast laser acoustics or laser picosecond acoustics or simply picosecond ultrasonics. So this is the field. Now, for example, let's see one typical experiment. We need a laser, for example, to excite the nanostrains, a femtosecond laser that illuminate the opaque material. There is the generation of these nanostrains that travel inside the material, and everywhere there is a pattern or different in acoustical impedance of material. There is an echo that comes back to the surface, and coming with a second laser pulse with femtosecond or picosecond or nanosecond delays depending of the distance and the sound speed, we can see modulation on the surface, either in reflectivity, either in deflection of the second beam, or there is a lot of different techniques where we can actually write as a function of time the arrival of this kind of echoes, and then we can do, for example, in imaging. So this is a very nice example from Ki Kun Sang in the National Taiwan University, where they are able, for example, to observe all this kind of subtle pattern inside the material, in opaque material, which is in the order of nanometers, as you see using this kind of technique. Now, how to measure? We can measure the fluctuation, as I have said, in the reflected laser beam intensity or direction induced by the return sound wave. For example, you do deflectometry, or such angular deflection fluctuation is caused by the protrusion produced when the sound wave reflects back to the surface of the material. Vibration amplitude of the surface of this kind of echoes is in the order of a few nanometers down to picometers. So it's not a very simple experiment. You need to have very good experimental tools and very good signal processing tools in order to observe that. Vibration of amplitude. So to take an idea of an experimental setup geometry of this kind of thing, you can read this red sentence that I wrote here. When we have an XY surface of the material and Z is the vibration axis, if the illumination region, which is in the order of 10 microns, 20 microns, was the area of Australia, for example, the scale-up displacement at the center can be only 1 meter. So we illuminate the Australia and we try to observe 1 meter vibration. So, where is the physics back of that? First of all, the physics is on the generation process of this kind of ultrasound. So, studying the vocal chords of the illuminated material. For example, of course, this depends on the light-sound conversion mechanism particular to the studied solid. And of course, there is a lot of physics in the detection process of material and the material diagnosis and how to explain our results back, because these are not static results. We have the time and the evolution in order to study the material in picosecond or femtosecond time scales. And there are here a lot of to read after by my transparencies that upload all this kind of points of physics back of this research. Now, let's focus now in the research, for example, to generate and control young nanoscale acoustic strains in semiconductors using chirped femtosecond laser pulse. And I can probe you that playing with chirp and different characteristics of the ultra short laser pulses, we can coherently control this kind of mechanical strains. For example, first of all, electron dynamics. The illumination of a femtosecond laser on a metal surface, for example, which metal surface is a very good transducer from optics to acoustics. We have electrons initially which are non-equilibrium. This is the Fermi distribution of electrons in the initial time scale, where we have some electron from here go to here, so there is a non-thermal electron gas on the illumination area of the metal. Then there is a fast thermalization with a different, of course, temperature on Fermi level. And then there is electrons in thermal equilibrium, of course. After the initial non-thermal electrons, there is also electron-electron and electron-photon interaction. And finally, we have electrons and lattice in thermal equilibrium, and there is a temperature of the lattice, which is actually produces the strain that propagates inside the material. Now, if you see the speed of electrons is initially the non-thermal is 10 to 6 meters per second, then the thermalized electrons are below 10 to 4 meters per second, and then the thermal diffusion is 10 to 100 meters per second. So non-thermal excitation, electron thermalization, and electron lattice thermal equilibrium. So what is the lattice dynamics? So here is a very nice thing where we illuminate the laser beam in a very small volume where we increase the temperature of the lattice as I showed you before, and there is a strain that goes outwards from the interaction region, and some of these strains go inside the material. So imagine that there is, for example, a thin metallic film and a substrate where we want to measure. So the strain propagates inside the material, and when it reaches an interface between the two materials, there is an echo going back, and the traveling wave travels through the second material. So when we have we can come with a delayed probe pulse illuminating the surface and measuring, for example, the difference in reflectivity when the echo arrives on the surface. So these are the lattice-induced strain, the strain propagation, the strain reflection from interface, and the detection of strain at surface. Now, the first thing, for example, of research is to searching for the best transducing material. Let's see, for instance, some two metals, titanium and gold. Titanium, if you see here, there is a very important parameter for this kind of transducing, which is the electron-photon coupling factor, the G factor as we call, where it is actually how fast transform the energy of the electrons to the lattice vibration. And if you see here, the titanium from certain temperature is, for example, 40 in this 40, 10 to 17, where in gold never reach in this area up to 1 or 2, 10 to 17. So there is a material, titanium, which have very high coupling, electron-photon coupling factor. Of course, titanium have a high stress yield, high melting point, large strains with no lattice damage. It is ideal as internal coating for nuclear reactor chambers, for example, if you see. Also, it's ideal as a buffer material for cooling by laser metal substrate system. And at the same time, it's a very good candidate for this kind of transducing. These are calculations by the group of Zingile in States. Let's see a typical experiment. Here is a typical Brillouin degenerate pump probe transient reflectivity setup. We have here a laser, a femtosecond laser. We split the laser, we have the pump beam and the probe beam. We modulate the pump beam and not the probe beam, and then we have measured the reflectivity change by differential photodiode with lock-in procession and a lot of difficult techniques that we do for signal processing. And we try to measure what? Here is the pump beam generates the strain. The strain propagates inside the multi-layer material. Here is the probe beam. There is a reflection of the probe beam from the interface surface, and there is also a reflection of the probe beam from the moving strain. Depending on the delay between pump and probe, there is an interference between these two reflections, which is an interference which is positive or negative, constructive or destructive interference, and this is actually the Brillouin scattering. See here for example, some results. Here we have silicon and titanium on it, or silver on it, another noble metal. Here is titanium and here is silver. This is the pump probe reflectivity measurement. So you see an abrupt increase of the reflectivity, which is the electron excitation. And then there is this kind of oscillating feature, which is actually the Bernoulli oscillation depending on the delay. If you see the difference between this, the period of these oscillations is in the order of 12, 13 picoseconds, which is actually the speed of the sound inside the material, the silicon. See now, if you do the same experiment, exactly the same experimental condition using silver, you barely observe this kind of oscillations. So here is clear that, for example, titanium is much more better transducer than silver for this kind of applications. But we want to do it also theoretically, to put the glasses, as Professor Nisoli said before, because we try to simulate this. The simulation of these effects actually are macroscopic equations, the so-called Anisimov couple equations, where simply speaking, the changing of electron temperature is because of electron diffusion, of interaction of electron with lattice, and also of the non-thermal electrons input on the thermal electron gas, thermalized electron gas. And here is formulation of this kind of interactions, where material 2, material 3, and of course are the materials, the different of the substrate. We can solve this kind of equation in order to calculate, for example, the lattice temperature and the strains and everything. And then if we know the lattice temperature, we have a spatiotemporal distribution of thermally induced lattice displacement, this equation, where we can calculate after the strain and the stress, and we can see in certain material, under certain illumination, under certain laser, under certain characteristics, if we have an explanation of this kind of effects that we have measured experimentally. See something. In silver, the maximum electron temperature is, for this kind of illumination, that in the experiment that I have shown you, in experimental condition that I have shown you before, is around 5,000 degrees. In titanium, it's less. But the thermalization common electron and lattice temperature in titanium is higher than the silver. And this is the important thing, because the strain is produced by the lattice temperature. So if you do this kind and calculate the strain, you see here, for example, the evolution. The blue is the titanium silicon material, and the red is the silver material, and you see the propagation of strain, and you see that there is a huge difference in strain because of this kind of effect, where the G factor and the interaction volume plays an important role for this kind of transfer. So there is a lot of research to, for example, to find the best transducing material from optical energy to mechanical energy, efficient transducer. Coherent control. Is it possible to optically control these strain pulses, to manipulate the light, and to control the nanostrains inside the material? This is from Gerard Mourou talk in the how to explain the chirp pulse amplification technique, where we have initially a short laser pulse generated by laser oscillation. We have the grating pair as a pulse stretcher, where we stretch the pulse in order to amplify it without destroying the material. We amplify, and then we have the grating pair pulse compressor to have again the Fourier limited pulse, which have high intensity and at the same time a lot of photons. So this is the Nobel Prize of Gerard Mourou CPA chirp pulse amplification technique. We have the same in every laser, femtosecond, titanium sapphire, for example, lasers, we have exactly the same scheme now. And in our lab, we can play with these two gratings, the distance between these two gratings. If you play with the distance between these two gratings, you can produce Fourier limited pulses. Positive chirp means the red pulse, the red photons of the pulse come first and the blue after, or negative chirp where the blue photons come first and the red after. So we can play with this kind of chirp parameters. Here is the CG parameters. Negative chirp means positive, negative C means positive chirp, equals to 0 not chirp, and positive is negative chirp. These are the explanation. So, we can measure actually the chirp by different techniques and see something. Is it possible to optically control? Let's vary the laser chirp. So, here are the results. Titanium on silicon now, same material. We try to play with the chirp. What we observe? Here are the oscillations in different chirps. You see blue is the negative chirp and red is the positive chirp and black is the Fourier limited pulse. If you see the Brillouin amplitude here with the same experimental condition, we do nothing in the experimental condition, just we change the distance between the grating and the compressor. We have seen that there is an optimum amplitude oscillation of strains when we have a bit of negative chirp. Not at Fourier limited as expected, but a bit of negative chirp. This is something that my PhD student measured that many times because I cannot believe that. But was there every time, even in different materials. Let's try now to explain this kind of behavior. These are something which is, for the first time, we have put in Anisimov equation the instant frequency. If you see the Anisimov equation and you read some books, you see that every time there is an envelope of a pulse. Never put the chirp inside to calculate lattice temperature, electron temperature, and things like that. So here is the instant frequency that we put here as a function of this kind of non-thermal electrons. We have put also the dose, density of state of titanium, and we can calculate actually everything using this kind of thermal equations, using this kind, and these are the results, the theoretical results. You have seen here that the negative produces higher strain than the unchirp, and a lot of much more higher than the same positive chirp. I mean, same chirp, but negative and positive. And if you do the calculation, you see here that the maximum temperature here is electron temperature is higher for the Fourier limited pulses, as we have seen in the experiment. Here, see here, the maximum reflectivity change is for the Fourier limited pulses, while for a negative and positive chirp, more or less we have the same behavior. But the thermalization energy between electrons and lattice is much more higher on negative chirp. Is the interplay between electron phonon lattice interaction and the photons. And we have a picture on that, a simple picture. I go, how much time I have? Okay, so here there is not the same to illuminate a Fermi gas of electrons when you have negative chirp or positive chirp. It's not vice versa. If you have a negative chirp, the blue photons come first. So there is a bigger area that electrons, because of Pauli rule, can absorb photons. Then the red photons find much more integration area in phase space or in E space, in energy space, in order to be absorbed and that transfer their energy to the material. The highest temperature electron temperature can be easily observed by the Fourier limited pulses, but the number of the electrons that participate in the excitation process is much more when we have negative CIRP than negative CIRP, and you see here by the interaction, by the area that of participation of electrons because of Pauli principle in this simple explanation picture of this kind of effects. So Fourier limited pulses is not every time the best pulse. So we need a bit of CIRP sometimes. But unfortunately for this process we need negative, because positive we can do very easily. We put a plate, we pass through the laser, but negative you need specially designed apparatus like multi-layer mirrors and things like that in order to do the negative CIRP. Now, these are the conclusion of my first part. So there is some reference that you can read from our lab where we are working on this kind of thing. Now, let's now limit ourselves on the surface waves that produced by laser on materials. Up to now we are speaking about the longitudinal waves traveling inside the material, but there are also other type of nano strains produced when a laser illuminated surface, and this is the surface waves. Let's see some surface waves. It's the so-called Rayleigh type waves, where in a Rayleigh wave, like sea waves, for example, we have this kind of waves, and each point inside near the surface doing a cycle, an elliptical motion. This is the direction of particle movement. And if you see the speed, the Rayleigh speed, depending on the Poisson ratio, is constant, completely different than the longitudinal waves, where there is an increase of speed as there is increase of Poisson ratio. How we can produce and control and observe, of course, this kind of waves on surface. First of all, we have non-destructive characterization of layer thin films. The propagation of surface waves depends both on properties of the film and of substrate, as we have seen. And there is a lot of applications because this kind of laser-generated surface waves depends a lot for thermomechanical properties of layer materials, thermal diffusion, optical penetration, material structure and composition, but also the parameters of the exciting pulse, including, of course, power, focus spot, pulse duration, CIRP. So it's worthy, maybe, to study this kind of effects, and laser is a good tool. Now, let's limit ourselves in nanosecond laser pulses. Why nanosecond? In nanosecond pulses, there is no difference between electron and phonon temperatures. Because, electron-phonon interaction time is in the order of picoseconds. So when we have a nanosecond pulse, everything is done. So actually, we can study only the bulk. We can study only the ions, not the electrons. So these we have a simple kind of thermal conduction equations, where the changing of temperature of the material is the diffusion. This is the laser source. This is the laser source. And here is something, for example, the so-called latent heat. Because when we illuminate with a nanosecond pulse, very easily we can go from solid to melt material, to gas, or to plasma. So we have to take in account all this kind of phase changes in order to study. And then we have the wave propagation equation, where if we know the temperature and the characteristics, Lamé constant and the thermoelastic coefficient of the material, we can calculate the time-dependent U displacement of the strain. So there is a combining method. We want to use interferometric phase method to observe at once a big surface amount on the material, and at the same time to be able to characterize vibration in the order of nanometers. So we need an instrument to see the Australia and observe 1 meter vibration of the Australia, at any point in the Australia. So this is actually the interferometric method. For example, here we have a nanosecond Nd:YAG laser where we can generate, we can pump the material, and then we can have with a phase interferometer, but these lasers must be single longitudinal mode laser. It's a bit crazy. Pulse laser and single longitudinal. Its technology can do that more or less with an external seeder where we can really have more or less one mode of vibration of the laser. So we have a very good, perfect, let's say, or very good plane wave of a nanosecond laser pulse. Doing this kind of phase interferometry, we can do the following, some signal processing. So here is the illumination area where we put 2 beams of the interferometer having a certain angle between them, and we have this kind of lines in purpose. Here we illuminate. Then we can Fourier transform in the K space from space to K vectors. And we have the DC component, the positive component, and the negative component of the Fourier transform. We can focus only the positive component, where we can do a phase unwrapping, for example here, and then we can do an inverse Fourier transform, and finally we can observe the illumination area is here, and here you see a cycle which is nothing else than the Rayleigh wave propagate outside of the surface of the interaction region. And the ability of this method was in the order of 1/1000 of the wavelength of the laser used. So it's something about 0.5 nanometers of this phase method. We can do also a FM model to calculate all the strains and everything like with the system before. So there are different excitation regimes. First of all is the absorption. Then we have a heat conduction, melting or plasma, depending on the laser intensity that we have used. Let's see some typical results. Here is the theory, and here is the experiment. Here is a real picture of the surface, 200 microns, but you can see here that this kind of surface waves is in the order of nanometers. Yet we can do actually cinematography of the Rayleigh waves of the surface in any time delay after the excitation that we want. Each experiment is one time, then we have to change position, and we are able to observe nanometer waves of an area that is many micrometers. And you see here, for example, here is different delays for different intensities, and you see here for example the formation of a crater here, which there is an ablation here after this delay. Here we are in elastic regime. There is some fitting of this kind of waves with theory and experiment, and we can explain well this kind of waves. See, for example, these are experimental results, the blue one. And here are experimental results of the surface of phase interferograms using this kind of laser. Now, of course, we can test the theory with some permanent features like white light interferometry that we have do in order to see the crater, to see the different structures and things like that produces after the illumination. And now we are switching in another thing which is more or less similar than the previous, where we have femtosecond excitation and nanosecond single longitudinal mode observation of the surface. Why nanosecond? Nanosecond for two reasons. First of all, single longitudinal mode you cannot have with femtosecond. You cannot have a plane wave with a femtosecond. And we need, of this kind of phase interferograms, we need single longitudinal mode. The second reason is that the speed of the sound of the Rayleigh waves on the surface, it's very, very slow. Nanosecond is more than enough in order to observe them. Okay? But why femtosecond excitation? Femtosecond excitation, we believed, and now we have the first proof that is completely different kind of excitation of this kind of Rayleigh waves. It's very much depending how fast you create this kind of waves. How fast you do that. And we have some first results published 2 weeks ago. So, what is also good? If you have a femtosecond and a nanosecond laser, it's very tricky, it's very tricky to control the time between them because the one is kilohertz, the other is hertz, sometimes different kind of pulse duration, different laser, flash lamps, a lot of different electronics. But if you are able to do that, you can do any delay you like. Because it's just, you have a femtosecond delta pulse and a nanosecond delay in any delay you like. You can play with your electronics and you do a cinematography, really cinematography of your Rayleigh waves. And this is the proof. Femtosecond excitation. Here you see the Rayleigh wave as it propagates outwards of the material in different time delays. So we can do really a cinematography, and these are proof of principle experiments in homogeneous materials. This is the first step. The second step is to try to put defects and different things. And the first is for defects is, so these are very experiments of the last 2 months where we are producing some defects here using laser, and you have seen that if we do nanosecond laser excitation of the surface wave, propagate of deep defects of the order of microns, 1 micron or more, propagates without, like the defect doesn't exist. So the depth, the coupling depth of the Rayleigh wave is inside the substrate in the order of few microns, as we calculate. If we use a femtosecond laser excitation, you see here, you barely see the Rayleigh wave, but there is nothing pass through the defect. So, and this is proved by also theoretically. We are able to stop the laser with very much surface defects. And you see here also some reflections, some diffraction, actually you can do everything you know in the macro acoustics, the same, because the physics is the same more or less, in the micro or nano acoustics, and you can play with this kind of strains. You can do anything you like. And okay, there is a new theoretical results using Lagrangian mechanical codes. We have a very strong group in our department that we do all this kind of calculations for thermomechanical kind of calculations, and to prove that we are really in a good manner. So this is actually the conclusion of the second part, that stabilized phase interferometer with single longitudinal mode are able to control this kind of wave, and also the physics can be explored by finite element analysis model, where we have good agreement, but also the important thing is that the excitation process, the pulse duration, the characteristic of the pulses can control this kind of strains. And now, because I'm not a material scientist, I'm a laser scientist, I welcome every one of you that you want to use this kind of techniques for material science, for example, applications on different materials and things like that, to probe a lot of different details on material structures. Thank you very much.
time for questions. Yes, please.
Yes, please.
Do you have ideas for real-life applications? Can you repeat it, please?
Can you repeat, please, the question?
Is there any applications in real life of this technique? This was okay.
Real life. First of all, the first application that is very known is the profilometry, fast profilometry. If you have a multi-structure material and you want to measure with an accuracy of few nanometers the multi-structure material, you can use this kind of echography of this kind of sound waves generated by the laser. The second application is to measure the elastic properties of unknown new materials. Even in graphene is very important because we know that graphene is a very good elastic material, but now we are planning to do experiment in order to explore how much you can go out in a graphene membrane, for example, how much you can go outside of equilibrium without destroying the lattice bonds. So,
But first you should find out few layers of graphene. Because
of course,
graphene properties
these are
changing.
Costas, these are details. These are details.
No, they are important details because they're different materials. That's
Okay.
why you're using graphite.
Okay.
It's different.
Okay. I can say to you another thing, which is I don't talk about that for here. It's a future emerging technology maybe, is the production of audible sound by the laser plasma acoustic generation on certain point, because there are now femtosecond lasers that are they have very high rep rates. I mean amplified femtosecond lasers. So we can have around millijoule in megahertz. So by encoding the repetition rate with a certain computer, you can do plasma with certain frequency. And by that, there are a group that I collaborate. Someone can speak, is the plasma microphone, by laser plasma microphone, and this 3D is surround. You can have the sound of source everywhere, back of you, in front of you, in an auditorium, up of auditorium, where you can produce it really music and high quality music using these laser sparks. So this is a practical application. Any other question?
Any other question? I have one.
Yes,
Because
Kostas.
I was very much surprised that you can produce a single longitudinal mode with a pulse laser. So my question is the following. If I will focus on the parameters that are happening within the gain material, or you have a very narrow spectral gain, or you have a very short laser cavity in order to increase the free spectral range of your longitudinal modes, so to isolate them. So, I mean, if you are doing something externally, you need something like a spectral filters in order to, but you're losing energy.
Yes.
Whatever. So what is the technique that you're
The technique,
externally?
the technique is external
So
seeder,
how much energy are you losing?
about 50%, which is not much because you don't need really energy for the interferometry. And this is something that is, it's commercial available, this kind of external seeder.
Compensation of the energy, no?
Yes, you have this compensation of the energy, and the price of the laser is double because of the external trigger and the single longitudinal mode. So these are some pictures of our labs in CPPL in Rethymnon in Crete. This is, for example, an interaction chamber and some credits. So thank you very much.